Okay, so we began talking about circular motion yesterday, and we talked about angular velocity, and also angular displacement. Well, there's obviously a third component. How does acceleration tie into all this? So we're basically just going to look at uniform circular motion. So in other words, we're going to be travelling with a constant angular velocity. Okay. Well, that therefore means that the linear velocity at any particular point will also be constant. Because remember, velocity was equal to the radius times the angular velocity. So if angular velocity is constant, the radius is constant. The linear velocity will also be constant. So you might be thinking, well, surely the acceleration is zero. But it's not. Because the difference now is that linear velocity is changing direction. So there is a change in the motion. So it's not in the magnitude of the velocity, but there is a change in direction which will create an acceleration. So here's our circle. So we're starting at A, and we're going to move to P. And we've got constant angular velocity. So at A, my velocity would go off at that angle, tangent at A. Whereas at P, it will be going off at tangent at P. So it's in a different direction. The magnitude's the same, but the direction is different. So what is the change? Well, if I consider them to be vectors, much like we did in complex numbers, where we treated the number as a vector rather than a number. And so there's my vector v, and v dash has the same length. Then the difference in the two must be the change. So in other words, yes, v dash, I've gone from the top of this triangle down here, but I could have gone down the v vector and then along the red vector and came to the same point. So my red one there represents the change in velocity. Now that angle there, it turns out to be theta. And we can prove that using geometry, but it will work out to be theta. Because remember, the radius is perpendicular to the tangent and all that sort of stuff. We could do it. Trust me, we could. Okay. So there it is. But it means it's going to be similar to triangle AOP because they're both isosceles triangles. And they both have an angle at the top of theta. Okay. So therefore the change in v over AP is equal to velocity over the radius. So the change in velocity is equal to the velocity times the length of AP over the radius. Now acceleration, we know, is the change in velocity over the change in time. So my acceleration now becomes v times AP over r times whatever the change in time is. Okay. Now, as the change in time approaches zero, then the length of the chord AP and the length of the arc AP would be getting closer and closer to being the same. So the acceleration we could consider then to be, because we're talking about at an instant, again if we use limits, limit as delta t approaches zero of the velocity times the arc AP, because as we're approaching zero I can say arc AP is the same as the chord AP. Okay. Well, the arc AP we can also rewrite as v times the change in time. Velocity times the change in time. Because if you multiply the velocity times the amount of time you've travelled, you must get the distance that you have travelled. So we end up with the delta t's cancel, v squared on r. But now there's nowhere to substitute the delta t into. So in fact it's no longer a limit, it's exactly equal to v squared on r. So the acceleration in uniform circular motion will always be v squared on r. The direction, if you have a look back at that red vector that I drew, of course on yours it's not red, but it always ends up pointing towards the centre of the circle. So don't worry, you do not have to derive it like that each time. we can simply say, well, okay, I know the particle's moving in circular motion, uniform circular motion, so I know the acceleration is v squared on r. We can just quote that, v squared on r. If we were talking about angular velocity, and remember angular velocity is equal to r times omega, then when we substitute that in, we get r times omega squared. So depending on what type of velocity you're using, which form you would. But I said the other day, we're more interested in forces. Well, force is just mass times acceleration, and you may even recognise this. Force is mv squared on r. mv squared on r. Or if we're talking about angular velocity, it's mr omega squared. That's what we call centripetal force. Okay, so we have a particle of mass m moving constant angular velocity in our circle. These are the parametric coordinates. Right, we're just travelling in a circle. So its x coordinate is r cos theta, its y coordinate is r sine theta. So the parametric coordinates of a circle. Okay. Show there is an inward radial force, mr omega squared, acting on p. That's just a fancy way of proving mv squared on r, or mr omega squared, and the direction is towards the centre, inward radial force. Now, I would not do it the way I just did it. Because we've got the parametric form, we're starting with displacement. So here it is, we're going around the circle. The x-coordinate, much like I did in projectile motion, I broke it up into its horizontal component and its vertical component. And I'm going to look at those independently. So there's x, it's r cos theta. Y is r sine theta. To get velocity, differentiate, but you'll notice I have to do it implicitly, because the variable is theta. But I want to differentiate with respect to time. So implicitly I'll multiply it by to theta to t. But the theta to t is angular velocity. And so it becomes minus r omega sine theta. And over in the y direction, a very similar expression turns out to be r omega cos theta. We want to prove acceleration. So differentiate again. I get minus r omega squared cos theta. But notice x is r cos theta. I get minus omega squared x. Now that seems awful familiar. What is it? Simple harmonic motion. Circular motion is simple harmonic motion. Right? Look what happens with the y. Same deal. We get minus omega squared y. Why is that? If instead of looking at the particle going around in the circle, imagine you were just looking at it and the circle was flat, what would you see? You'd just see a particle going backwards and forwards, backwards and forwards, backwards and forwards. And it doesn't matter which direction you look at the circle, it's always going to look like it's doing simple harmonic motion. Okay? Now, remember, we wanted to prove it was the mr omega squared. So let's resolve these accelerations. Acceleration will be the hypotenuse. So it's going to be the x acceleration squared plus the y acceleration squared. I end up with x squared plus y squared, but we know x squared plus y squared is the radius squared, and there it is. Acceleration squared is omega to the power of 4 r squared, so acceleration is r omega squared. We also had to prove that it was directed towards the centre. So there's my force, mr omega squared. Well, the angle that it makes would be the inverse tan of y double dot on x double dot. Well, y double dot on x double dot is y on x. Well, what direction's that? Well, it's theta. Go back to our triangle. The inverse tan of y on x is, in fact, the theta. So the angle is going to the centre. It's along that same line. So that's probably the easier way of proving that, if we start with the displacement equations. All right, then, let's have a look at this telecommunications satellite, eh? Orbits Earth, constant angular velocity, gravitational force is am on r squared. By considering all the forces on the satellite to be negligible, we're going to prove that r is the cube root of a on omega squared. There's Bob. Okay. The resultant force. Now here's the thing with circular motion. The resultant force in circular motion is centripetal force. Centripetal force is not actually a force by itself. It is the reaction of the change in those velocities. So it is a resultant force. And it's always directed towards the centre. Well, when I'm just drawing Bob, I suppose I could draw it anywhere because I'm just saying I'm going to the centre. So I've made it go down here. And so my resultant force, which I know is mr omega squared because it's in circular motion. Gravity is am on r squared. So I'm looking at the instant where we're going straight down. So mr omega squared is equal to am on r squared. Oh, by the way, I should have said, why can I say gravity is always in the same direction as the resultant force in this case? The centre, exactly. And in this case, we're orbiting the Earth, and gravity is always directed towards the centre of the Earth. So they'll always be in the same direction. So mr omega squared is am on r squared. Tidying that up, r cubed is a on omega squared. There's our answer, the cube root of a on omega squared. Okay, string, 50 centimetres long. It's going to break if we hang a mass which is more than 40 kilograms. The string will just go snap. A mass of 2 kilograms is attached to the string. Hey, so now it's not going to break. You little beauty. So to celebrate, what do? Spin it around in a circle. Yeah, it's not breaking. It's not breaking. Oops, it broke. Why did that happen? I could hang one 40 kilograms, 2 kilograms, now my string breaks. Well, let's see why. Here it is just hanging straight down. So I'm going to say, well, resultant force again I'm going to make just going straight down. In this case, it's not circular motion because I'm just holding it and it's hanging down. Gravity, though, is still acting in the same direction. Oh, here's a new thing, T. Remember, there's always a resistive force. When you have something attached to a string, that resistive force is called tension. So you always have tension going away from the object, in this case, up the string. So mx double dot is equal to mg minus t. 0 is equal to mg minus t. 0? Yeah, because it's just, I'm not doing anything with it. It's just hanging there. Nothing's happening. So there is no acceleration. So the tension, I can calculate how much tension this string can handle. It can handle 392, the units for force is newtons. Also is kilograms metres per second squared, but newtons is easier to say. Okay. So I now know how much it can handle. So now when I go and spin it in the circle, now I'm spinning it in a horizontal circle, but now it's performing circular motion. So towards the centre is my resultant force, but that is centripetal force now. I will still have tension in that string. There'll be nothing to do with gravity though, because that's vertical. So I know that that tension will equal mr omega squared. I can now work out how fast I can spin it before it breaks. The tension we just worked out, it can handle 392 newtons. Sub it in. The mass now is 2 kilograms. Radius is 0.5. There we go. 2 root 98 radians per second we can spin it at before it snaps off. How many times are we spinning it in a second? 2 times root 98. Oh, 20 radians. 20 radians per second. Now how quick is that? 20 radians. How many revolutions is that? 20 divided by 2 pi. Come on, my arm's killing me. This thing's going to break soon. How many? 3 times in a second. Well, yes. All righty.